Alright, hello everybody. We will continue our lecture series. And last lecture we saw this the concept of calculus of variations, extended that to constraint optimization problem as well as we discussed about an example problem which motivated that this concept of variational calculus can be used for optimal control very well directly rather. So, now we want to generalize this concept and then talk about how do we formalize this optimal control concepts coming from calculus of variation. Okay. So, we will try to use these Yale equations again, but now it will be in the fully framework of optimal control theory again. I mean, we do not want to talk in a disguised way and think like that anymore. We will define an optimal control problem and try to attempt to kind of solve this problem as it is actually. Okay. Alright. So, what is the summary of variational problems in multiple dimension with constraints that is what we are looking for, that is what we discussed in the just in the last class. That we were interested in optimizing this kind of a cost function along with this general equality constraint sort of thing, where x happen to be n dimension and phi happen to be n tilde dimension. And then we talked about this Lagrange existing theorem and things like that, and ultimately led us to this definition of this L star. Okay, again this L star happens to be a function of lambda also. So, this L star can be defined like this, and then we have this Yale equations. Okay, and this Yale equations happens to be something like this actually. Okay. So, you have n equations coming from there and tilde equation coming from there, and transversality conditions were like this. Okay. We discussed everything in the previous lecture. Some of you who do not recall probably can revise that actually. And then ultimately led up with this kind of Yale equation with transversality conditions. Okay. So, this transversality condition depending on whether TF is fixed or TF is free, we have these two class of different things, and we discussed about that in the last class. So, ultimately the key point is we have Yale equations, Euler-Lagrange equation, and there are transversality condition or boundary conditions like that actually. Alright. So, now how do we use these concepts for this application of these ideas for optimal control problems rather. So, what is the formal definition of optimal control? That also we discussed in the last class a little bit towards end of the last class. But I mean, to revise it again, what you are looking for is to find an admissible control ut, okay, which causes the system this x dot equal to f of x u t, where initial condition is fixed, okay, to follow an admissible trajectory that optimizes the performance index on the way while satisfying the appropriate boundary conditions. So, these are the features of a good optimal control problem definition. You need to have a state equation, system dynamics, you need to have initial conditions or rather final condition, initial condition together, that means appropriate boundary condition. And as a designer, you should always try to construct a cost function that you want to minimize or maximize either way, okay, which will lead to the objective basically. Okay. So, these are the three components that is always essential for a good optimal control problem formulation actually. Okay. Alright. And also remember, now if you look at this thing, okay, this constraint equation contain an x dot term, okay, x dot t equals 0, whereas this constraint equation what you are talking here, okay, I mean this cost function, okay, let me go back to cost function also there, okay, cost function contain an x dot term also here. Now, this cost function what you are looking for here typically does not contain an x dot in most of the cases, okay. But x dot is also required because x dot comes as part of the state equation. Okay. By the way, it does not mean that you do not really need x dot all the time. I mean, you can have a problem where x dot is also there. Okay. And in especially this LQR class, linear quadratic regulator class, when we discuss that point of time, we will see that there is a class of problem for which you really need x dot in the cost function also. But in general, most of the time you do not need it. It is sufficient to define in the form of x and u. Because once x and u is there, then x dot is constrained anyway like this. You do not have a freedom of, you do not have further freedom basically what I mean. Once you get x and u and the initial condition is defined, then this x dot happens to be equal to that. Okay. So, you do not have too much freedom for minimizing, maximizing of that quantity basically. So, that is the reason why you are not putting it here most of the time actually. Alright. So, this is the problem definition there. Okay. So, how do you go and do that? Okay. Now, the problem here is this particular term, I mean if you see this equation, okay, what we discussed in the calculus of variation setting, it did not contain any term outside the integral. Okay. But suddenly we are talking a term which is outside the integral actually. Okay. This term which is outside the integral. How do you handle that? Okay. Alright, so one way to handle that is something like this. Let us first consider this integral. Okay, we will consider integral T0 to Tf d by dt of this quantity. Okay, and this happens to be like that. Okay, this function evaluated at final value minus evaluated at initial value. That means this function what you are looking for, this phi of T of xf, small phi of T of xf, that is what you are looking for. This can be interpreted as something with this one plus the integral of this quantity. Okay. But once you evaluate any function with a number, okay, this particularly will give us a number basically. Okay. So, that means that is irrelevant for optimization really. Okay. You are talking about this one plus something actually, okay, which is variable. Anything that is that has some flexibility, we can do something for minimizing or maximizing. Anything that is a number, we can't do anything too much on that. So, that means what I mean is this phi of x0 t0 is a constant value. So, instead of trying to optimize this j, okay, it is equivalent to optimize j1 ignoring this fellow. Okay. So, we will ignore that and then tell okay, now this is integral of that, and that is the original thing is also integral of that. Okay. There is a term which is inside the integral, and the outside this is gone anyway, there is integral term. So, I will combine these two. Okay. So, this what you are looking for here now is compatible to what you have seen before actually, right. This does not have anything outside. Okay. So, this is what you are this is the trick that we are following here actually in a way. So, instead of trying to optimize the cost function j directly, which is also possible. I mean, I will talk to you in a few slides down the line actually. Okay, that is another way of doing things. But we will consider a one-to-one equivalent of what we already know, and how do we want to put it in that framework actually. Okay, then we do this algebra and then tell okay, this is just a constant value, it does not matter. So, we will ignore that and then construct this j1 and then take both the terms inside the integral. Then it happens to be very compatible to what we already know basically. Okay. So, now we can use this calculus of variations ideas that we already know. What is that? Then obviously, we will construct a j bar first, and j bar is nothing but whatever we already have inside the integral plus lambda transpose this constraint equation. Remember, f minus x dot equal to 0. Okay. We have this constraint equation, right. So, f minus x dot will be equal to 0, and that constraint equation should come here inside the integral actually. Okay. Now, the further algebra talks something like this, wherever you do not see any derivative term, you define that as something like Hamiltonian. Okay, this definition comes from Pontryagin ideas and all that one. That history and all I will not talk here, but it essentially comes from his ideas basically. So, anyway, before that people were all talking about EL equations and going directly there, but this particular concept of simplifying things and all that was a great contribution from Pontryagin actually. We will see some of his other contribution in constraint optimal control lectures later actually. Okay. But anyway, coming back, this Hamiltonian is defined as something like this, all the terms without derivative terms. Okay. Then I can simplify j bar, okay, as something like this, because L plus lambda transpose f is nothing but h. Now, I will drop the arguments for simplifying simplicity of algebra. I know that which one is a function of what. With that assumption, I will drop this argument, okay, and then tell okay, this is first h, and then the next term is d phi by dt, then the next term is this quantity lambda transpose x dot. Okay. So, this is my quantity. So, this is nothing but my L star actually. Okay. So, j bar is nothing but integration T0 to Tf L star dt, where L star is nothing but that. Okay. Now, it is very compatible to what we know before actually. But what is L star, I mean what is Hamiltonian and all? Remember, Hamiltonian is a function of x u and lambda, and L star is also a function of x u and lambda actually. So, we have to apply the EL equations thrice, once with respect to x, once with respect to u, and once with respect to lambda actually. Okay. Alright, so we will do that, and then this L star, I mean just to summarize, L star is defined like this, where h is defined like that. Okay. H is L plus lambda transpose f, where L star is nothing but h plus d phi by dt minus lambda transpose x star. Now, what is the necessary condition? We have to apply these conditions thrice. Okay. And again this expression nowhere contains u dot and lambda dot. So, these two quantities will go to 0. Okay. But we are not done yet, because this algebra we have to cater for actually. Okay. So, what is the del L star by del x? Del L star by del x. So, that by definition is del by del x of L star, and L star is nothing but this quantity, right. So, we substitute this quantity here, okay, whatever L star is defined is here, and then we carry out this algebra. So, first thing talks about del s by del x, okay, plus del by del x of this quantity whatever you have here, and d phi, okay, is nothing but del phi by del t plus phi is a function of x also basically, right. So, del phi by del t plus del phi by del x transpose times x dot actually. So, these two quantities comes from this quantity really, okay, and this quantity does not contain any x or I mean lambda. So, the derivative of that with partial derivative of that with respect to x is 0 basically. Okay. So, we left out it like that. Okay. Then this is del h by del x plus this quantity del square phi by del x del t plus this quantity del square phi by del x square into x dot. This is double derivative sort of thing actually. Okay. Now, what about the other quantity? This is one quantity. What about the other quantity del L star by del x dot actually? This is the first quantity that we discussed. What is the second quantity? D by dt of del L star by del x dot. So, that is what d by dt of del L star by del x dot. Okay. Now, we have to go to this this L star sort of thing, okay, and okay, d by dt of that, and d by dt of that is nothing but d by dt of del phi by del x minus lambda basically. Okay. Right, because it is very easy to see that from L star definition is something like this. Okay. So, you can think of this the del phi by del t is something like this, again I explained that here. Okay. When you talk about d phi by dt, sorry, this d phi by dt is nothing but del phi by del t plus this term. So, that is where you get an additional x dot actually. Okay. So, now when you talk about del L star by del x dot, you are actually looking for this expression. H is not a function of x dot. So, any partial derivative with respect to that is not there, okay, but it will come from these two expressions. Okay. What is these two? One is del phi by del x, the other one is lambda, okay, that will come here, and d by dt of that you have to take. So, d by dt of that is nothing but again del by del t of that plus del by del x of that times x dot. Okay. Whenever remember whenever you talk, there are two things going on here. One is the total derivative, something like d phi by dt. The other one is the partial derivative, something like del phi by del t. So, whenever you have a d phi by dt, then the first is the partial derivative with respect to the free variable, and then you have to account for the chain rule of derivative as well basically. Okay. So, that is how the algebra will proceed actually. Sorry. Okay. So, this is what you are looking for here. Okay. So, d by dt of that it turns out to be like this actually. Okay. Remember, because del by del t of that one, okay, plus del by del x of that into x dot, okay, minus this d by dt of lambda, which is nothing but lambda dot. That term, that because this expression, just look at this expression, and whenever you have this del L by del x actually, we have to worry about that kind of thing. Anyway, so this is the type of expression that I was talking about. Okay. So, do the algebra yourself, then you will be, the clarity will emerge actually. Okay. Then ultimately you will end up with something like this. Okay. So, what is the EL equation? EL equation tells that this term minus this term has to be equal to 0. So, when I talk this term minus this term, obviously these two will cancel out, del square phi by del x del t is there both the places, it will cancel out, and then you will be left out with other term. That is what it is done here anyway. Okay. So, one term will cancel out, the other term will tell us that del s by del x, okay, from here, okay, okay, the other term will also cancel out, okay, these two terms, okay, this is same as this actually. Okay. So, then we are left out with nothing but del h by del x plus lambda dot equal to 0. So, that means lambda dot is nothing but minus del h by del x actually, and this particular equation is called co-state equation or adjoint equation really. Then coming to the second part of the equation, del L star by del U equal to 0, that is easy. Okay. That will nowhere else U appears. U appears only in the definition of Hamiltonian. So, what you are telling is del H by del U has to be equal to 0. Okay. And then del L star by del lambda will nothing but the this constant equation sort of thing. So, it will give us this thing like that, del H by del lambda minus x dot equal to 0. That means x dot is nothing but del H by del lambda. And when you talk about H is like that, so what is del H by del lambda? It is nothing but f. So, x dot equal to f of x ut, that is nothing but your state equation. Okay. So, ultimately what you are looking for is what you are landing up where we landed up is something like co-state equation, an optimal control equation, or is also called a stationary equation, because this is just an algebraic equation sort of thing. Okay. And then this is there is a state equation actually. Okay. So, this equation has to be solved together basically that way. So, this is what is summary. Summary is you have to define Hamiltonian, which is nothing but L plus lambda transpose f, and then carry out this algebra where one thing is x dot equal to f of x u, state equation, and then del h by del u equal to 0, optimal control equation. Once you solve this equation at every point of time, u will be a function of x and lambda ultimately, because Hamiltonian is a function of x, u and lambda everything. So, if you solve this equation, okay, for u, then you get the optimal control, but for solving that, you remember u will be a function of x and lambda both, and for that you need these two equations together basically. Okay. So, one part of the equation is called state equation, the other part is called co-state equation. Okay. Okay. More on that I will talk in a 1 or 2 slides later actually. Okay. Now, what about boundary conditions? Okay. Boundary conditions are, again we go back to that the transversality condition and all, general transversality condition happens to be like that, but L star remember is something like this. Okay. This is that where d phi by dt is nothing but del phi by del t plus del phi by del x into x dot sort of thing that way. So, you substitute this L star wherever you see L star is something like this, and then you get for variety of conditions this way that way and all, you can derive anything actually. So, for example, when both t naught and x of t naught are assumed to be fixed, then this delta t naught and delta x naught, those are 0 by default. So, we will end, all that we have is delta xf and delta tf, that the variation there actually. Okay. Alright. Now, what you do is you substitute these expressions del L star by del x dot and things like that, you then carry out this algebra a little bit more, you cancel out some of these other terms and end up with some expression like this actually. So, what I mean is whenever this t naught and x of t naught are assumed to be fixed, which is many of the times it is true, then this is the boundary transversality condition. Ultimately, this simplifies to something like that in the form of Hamiltonian actually. And in addition to that, many times people tell, okay, sometimes this is like delta xf is 0, that means xf is fixed, then this only this one you left out, your delta tf is free, that means Hamiltonian at the final time is nothing but minus of del phi by del t. And similarly, when tf is fixed but xf is free, then this is 0, but because this is free, this cannot be 0. So, you have lambda f equal to del phi by del x of actually. This is what is extra here. If when tf is fixed, xf is free, you will end up with this equation. That is what I just now described. Okay. So, that means lambda f will turn out to be del phi by del xf actually. When on the other hand, when tf is free, but xf is fixed, then h of tf will be minus del phi by del t evaluated at tf. Okay. And when both are free, you will have both things necessary anyway. If your xf is free and tf is also free, then both these conditions will come into picture. Okay. But also remember, how many conditions are those? Those phi is a scalar, x is a vector. Okay. Del phi by del x happens to be n. So, that means you are getting n boundary conditions from here. How many differential equations you have here? It is also again n. H is a scalar, x is a vector. So, lambda dot is of same dimension as x actually. So, that means lambda is also same dimension of x. In a way, you can argue that way actually. So, essentially what is going on here? We have a problem, optimal control problem, and we have a bunch of differential equation, bunch of algebraic equation, bunch of boundary conditions and things like that, and all of them have to be satisfied for a meaningful solution basically. Okay. Now, what about an alternate approach? We do not have to carry out all this longhand algebra and things like that, but in a simplistic sense, let us see whether you can arrive at the same solution or not actually. So, the performance index to be minimized happens to be like this, the same performance index that we started with. Path constraints are nothing but the state equation, again boundary conditions are there, x of t 0, x of x 0 equal to x 0, I mean the initial condition which is specified, and T f is fixed and x of T f has to be free actually. Yeah. Anyway, so this is what it is. Then the necessary conditions of optimality, what we do? We will not worry about this calculus of variation EL equation and all. We will go back little further, I mean little more before that. Then we will construct an augmented performance index J bar, which is nothing but that. So, L plus lambda transpose f minus x dot. So, remember f minus x dot happens to act along the path. So, I will take it inside the integral, which is path dependent cost actually. Okay. Very same thing as Lagrange idea, okay, that put it as J bar is something like this. Then directly define Hamiltonian like that. Hamiltonian is same Hamiltonian what we discussed, L plus lambda transpose f again. And now we are interested not applying in EL equation, but we will consider first variation of J bar directly. Okay. When you do first variation of J bar is nothing but first variation of phi plus first variation of this integral. And remember a very fundamental theorem of calculus of variation that we discussed that time, that variation of integral is the integral of variation actually. Okay. So, we will excite that actually here. So, and then take this variation inside the integral. Okay. So, then we talk about this algebra, that variation of these terms can be expanded, and then you can write variation of this is nothing but variation of Hamiltonian plus variation of these two multiplication quantities, that means variation of this and variation of that. Okay. Okay. So, essentially the first variation del J bar happens to be like this, and now you look at the individual terms. Okay. Del phi is nothing but del phi. What is del phi? Del phi can happen through variations of x f actually. Okay. So, del phi is nothing but del x f transpose times del phi by del x f, I can write it that way. Similarly, del h I can write it that way, del h is nothing but, remember h is a function of x, u and lambda, all the three quantities actually. Okay. So, then variation of h can happen through variation of x, through variation of u and through variation of lambda as well. So, then this essentially contains these three quantities. What about the next? Next is that. Okay. That one we will consider with integral term. So, this with integral, this is what it is, and this is nothing but by definition delta x dot is nothing but dy dt of delta x actually, this by definition of delta x dot. Okay. Or you can excite this another calculus of the variation result, that variation of derivative is nothing but derivative variation, that we also discussed there actually. So, variation of derivative is nothing but derivative variation actually. Okay. Then it is we are ready for applying this this partial what is this integration by parts, and then this is nothing but this first one, then the integration of the second one with respect to time is nothing but delta x minus derivative of first one into integral of the second one. Okay. So, this is what it is. So, ultimately it leads to this this expression of lambda f transpose delta x f, this expression evaluated at T f at delta x f, and minus this expression evaluated at T naught delta x naught actually. This is what it is. Minus of this quantity now can be interchanged, I mean because it is something like x transpose y, when x is a vector, y is a vector of the same dimension, then x transpose y is nothing but y transpose x. Ultimately it is nothing but x 1 y 1 plus x 2 y 2 plus x 3 y 3 like that. So, you can exchange it and tell x transpose y is nothing but y transpose x actually. Yeah. So, that is what is going on here actually. Okay. Just for I mean further simplicity, we require this delta x term on the left hand side to be compatible with all these expressions that we have been doing. And if somebody can do other way around, which is also true, the delta del phi by del x f transpose times delta x f like that actually, then you do not need this algebra. But anyway, we have been doing in the left hand side variations first. So, we will be compatible with that actually. Okay. Just to do that, it is put that way. Okay. Okay. And one second, the small mistake again here. This transpose is not required. Okay, this transpose is also not required. Okay, because it is X transpose Y is nothing but Y transpose X. So this X transpose Y is nothing but Y transpose X actually. So that's nothing but lambda dot. The transpose will not be there. Obviously, the multiplication has to be a scalar. So that also needs to be looked at actually. Anyway, so this is what it is. So this integral happens to be something like this. Okay. So we'll put them together and tell, okay, this first variations, all the quantities that we know, this is first variation of phi, so let it be there, and then first variation of all these other quantities, lambda, I mean Hamiltonian, these three terms, and then the other quantities are put like this actually. Okay. Remember, this term will go to this term outside the integral basically. So that's how it is done. So what you are looking for? The first variation, if you collect all the terms and try to put it together, the first variation del j bar happens to be something like this, delta x f transpose times this plus integral of all this and then plus integral of that actually. So again this leads to that we have to assure that the first variation happens to be 0 and it happens to be 0 for all possible variations of this x I mean x u lambda delta x f everything actually. That means the coefficient needs to be 0. Okay, so this coefficient needs to be 0. This is the fundamental theorem that we discussed in the calculus variation class also. Okay, if it for all variation that one function is not 0, then the other coefficient has to be 0 in the interval and all that actually. That theorem you can revise also if necessary. Okay. So what you do is all the coefficients happen to be 0. So the coefficient means whatever whatever results from here, we will see that in a second actually. So what results from here? This particular equation. X dot is nothing but del h by del lambda, and what is Hamiltonian? Hamiltonian is L plus lambda transpose f. So when you talk about del h by del lambda, then there is nothing but f actually. Okay. So that's what we are doing here. So x dot equal to del h by del lambda, okay, from here, and that is nothing but f. Okay. So that means x dot equal to f actually. Okay. There is nothing but state equation. Similarly, if you talk about this equation, lambda dot equal to minus del h by del x, what we derived just before. Okay. Similarly, if you take this coefficient, it is nothing but del h by del u equal to 0, what we already derived again actually. Similarly, the boundary condition, this will come from here, lambda f equal to del phi by del x f. Okay, we have not considered other generic boundary conditions and all, we have considered where Tf is fixed actually. So that is how it landed up here actually. Okay. Alright, so this is what the summary is. We have this bunch of equation that needs to be satisfied ultimately. What is that? The first is state equation. Okay. The second is co-state equation. And remember, the dimension of co-state is same as x basically. And then third is optimal control equation, del s by del u equal to 0. And the fourth is boundary conditions, I mean whatever associated boundary conditions actually. And remember, if any of these equation is not satisfied, then it is a non-optimal solution, not really an optimal solution at all. Okay. So for an optimal control to be, for a control to be an optimal control, all these equations has to be satisfied simultaneously actually for the entire duration T naught to Tf. Alright, now this is the problem what we call as kind of dualization and things like that, because for solving an n dimensional problem, we actually look for differential equations in 2n dimension space actually. Okay, this is n dimensional differential equation here and n dimension coming from here actually. Okay, but the thing is this boundary condition, I mean this differential equation is available along with this boundary condition, and this differential equation is available along with that boundary condition. Okay, so boundary conditions are available. It's a matter of only accounting for that actually properly. Okay. Alright, so what you can see here, that's what I am telling here, let me just do that. These two conditions, what you are looking for, okay, these two are compatible and these two conditions are also compatible. Okay. Alright, and this equation has to be solved for our optimal control. Okay. If you solve this algebraic equation, you will become a function of x and lambda at any point of time. To get that x and lambda, we have to use this differential equation set along with their boundary conditions to have an idea of what is x and what is lambda at that point of time actually. Alright, some of these comments are given here. So, the state and co-state equations are dynamic equations. and optimal control is a stationary equation obviously. And the most problematic or rather painful part is something there. We know that differential equations and boundary conditions are available, that is not a problem, but we simply cannot take any numerical integration algebra like algorithm like Runge-Kutta 4 and things like that and then start propagating it. It is not possible because the boundary conditions are not given at the same time. Okay. That is the very critical observation actually. If the boundary conditions are available at the same time for all the variables, then you could have simply integrated it either forward or backward, that is not a problem. But the point here is you have two n differential equations, but n differential equation conditions, initial condition, I mean for boundary condition sense, for n differential equations you have initial conditions, conditions are given at T naught. For rest of the n differential equation, the conditions are given at T f rather. Okay. So, that is where it leads to this difficulty of something called 2-point boundary value problem. Okay. So, for solving that we need this iterative solution procedures mainly because of that actually. Okay. What is another observation? You can see this boundary condition the way it is given, the state equations initial condition is given, that means it develops forward, where the co-state the final boundary condition is given. So, that means this equation develops backward actually. You can integrate it backwards. Okay. And remember eventually what I am talking about is lot of numerical intensive algorithm, iterative solutions and all that, and that is why this becomes computationally kind of a very complex actually. Okay. They are computationally intensive and you really require iterative numerical procedures to solve it actually. Okay. And even if you solve it, this iterative procedure, okay, one very intuitive thing is, okay, I do not have the initial conditions for lambda, but let me guess initial conditions for lambda, and then the initial conditions for both x and lambda will be available. Then I can integrate it further, and at t equal to t f, I will see what my integrated value of lambda is and whether it satisfies this equation or not. If it does not satisfy, I have to come back and correct it my control history in such a way that that will try to satisfy in the next iteration basically. Okay. So, that kind of ideas are something called suiting method and all, we will also talk about that in the next class actually. But there are other ways of doing that as well actually. Okay. So, coming back to the point here is we really require to solve 2n differential equations, and this process is called dualization actually. That means you are this lambda happens to be operating in the dual space also in a way. And you got 2n dimensional differential equations to cater for. So, this you are actually landing up with the dualization of a problem actually. Okay. And this dualization problem is difficult because it leads to this 2-point boundary value problem. And one more comment on the way is this state equation happens to be stable, most likely this co-state equation will happen to be unstable actually. Okay. So, just now the idea that I told that okay, initially you guess some lambda 0, integrate it further and all, it is not really very good, because what you are talking about for a stable system, this equation is anyway unstable, and any amount of unstable differential equation numerical integration, the error of initial condition guess will be amplified quite heavily basically. Okay. That means to a pictorial sense, if you have some unstable differential equation, if you start with this initial condition, suppose it blows up that way, then if you start a little bit differential equation, it will go that way. Okay. That means the separation between them happens to grow quite a lot actually. That means the error value gets amplified as well basically. Okay. So, that is the problem of even numerical integration actually. Okay. And then there are ideas of multiple suiting and all. Okay, do not suit it too much, do not propagate it too much, you break the trajectory into parts and all that. When you break it again, it has its own difficulties. How do you assure continuity, smoothness and all that? Those things we will discuss in numerical method procedure class. Anyway, all these things are given here. And also remember, after all these difficulties, suppose you are able to solve it, okay, ultimately you are solving it for a particular, okay, what you are doing here, okay, if you are solving it, you are solving it for a given initial condition only basically. That means we are actually solving an open loop control strategy. Okay. The control is not in closed loop sense basically. So, these are the difficulties of optimal control problem formulation in general. Problem formulation is nice, but you will end up with this computational difficulty issues and all that. So, this problem is called this so called curse of complexity actually. Okay. So, this is what you are looking for is you are ending up with a situation you have to deal with a complex problem actually. So, instead of n dimensional problem you will end up with a 2n dimensional problem, and then the boundary conditions are split, then the nature of the differential equation is opposite, okay. And then unless you solve it you do not get a control anyway actually, it leads to a lot of iterative procedure and things like that way. This is called curse of complexity, okay. Alright. So, ultimately even if you do all that, and finally you will it leads to this open loop control solution ideas actually. Alright, on the way there is a different comment here. One theorem tells that if the Hamiltonian h is not an explicit function of time, then h has to be constant along the optimal path. Okay. Why so? Because now you can tell dh by dt is nothing but del h by del t, okay, plus, okay, these variations coming through this x, u and lambda. So, x dot transpose times this plus u dot transpose times that plus lambda dot transpose times that and all that actually, okay. Now, you can combine these two quantities, okay, this x dot transpose times del s by del x, okay, plus this lambda dot and all that actually, because see del h by del x, okay, del s by del lambda is nothing but x dot, okay. So, and you remember lambda dot times lambda dot transpose x dot is nothing but x dot times lambda dot x dot transpose times lambda, I mean lambda dot actually, okay. This algebra what you are looking, del h by del lambda is nothing but x dot, and lambda dot transpose times x dot is nothing but x dot transpose times lambda dot. So, if I do this algebra and substitute it back here, then I can observe it here, okay. Then I tell, okay, this is nothing but my co-state equation and this is nothing but my optimal control equation, and I am working on the optimal path anyway, that means all these equations are satisfied. Once it is satisfied, then dh by dt is nothing but del s by del t, okay. And that is equal to 0 because by definition h is not an explicit function of time. So, any partial derivative of h with respect to t is 0, that means ds by dt happens to be 0. That means what does it tell you? It tells us that if h is not an explicit function of time, then h has to remain constant along the optimal path, okay. And typically for a regulator problem and all we will see that h is not only constant, but that constant happens to be 0 also basically, because h will become 0 at t equal to infinity, but h is a constant anyway, okay. So, if it is 0 at one point of time, then it has to be 0 everywhere actually, okay. So, using that idea, then it turns out that in general h is constant value for whatever problem is that on the optimal path, as long as it is not an explicit function of time, and most of the time we do have such a similar situation actually, the state equation and all will not be explicit function of time, constant parameters especially time invariant systems and all when you talk about that. Okay. So, for those class of problems h has to be constant, and that can be a verification tool in numerical solution procedures also. Once you get a solution, you can plot h versus time and have a feeling whether it is constant or not actually. This can be a verification tool. Anyway, so coming back to the general boundary condition or transversality condition and all that. So, this is what it is. We can the similar ideas that we discuss in calculus of variations, we can talk here also. It starts from something like this, and then depending on various cases, case 1, case 2, case 3, all that, you can derive the corresponding equations and all. Primarily, we are interested in these two cases most of the time. So, one case TF has to be fixed, other case TF is free, and TF fixed and XF free, then you from here you can see that TF is fixed. So, this is 0. So, you end up with something like this. So, that means lambda f is nothing but del phi by del xf. And second case TF is free but XF is fixed, okay, that is a kind of a hard constraint formulation you can think about with free final time. Time does not matter, but ultimately the error has to be 0, that kind of situation. Then this part has to be 0 actually, that means h of TF is del phi by del TF rather here. Okay. So, this is how you would use these conditions as and when it is necessary in a particular formulation actually. Now, with all these in ideas, all this in mind, especially these conditions and all, we will discuss this some example problems again to get our ideas clear. Okay. First, we start with something called a toy problem. It is not really very challenging, but it gives us some clarity about how do you use this for these ideas and all. So, let us start with this. This x1 dot is x2 and x2 dot is minus x2 plus u. I think problem cannot be more simpler than that. It's actually a linear second order linear equation actually, okay, system dynamic sense. Okay. And J is nothing but this kind of thing. So, what you are looking for is at t equal to Tf, and Tf is nothing but 2 actually, that is also available. At t equal to Tf, our state values x1 and x2 should remain close to 5 and 2. Okay. We are not interested in exactly meeting 5 and 2, as long as these terms are minimized, we are okay actually. That means, you can start with this initial condition which is 0 0, okay, this okay, you can start with this initial condition 0 0, and at Tf t which is Tf, t goes to Tf, okay, and our value, okay, has to be something like, okay, if you are plotting, okay, you are plotting in terms of x1 and x2, let us say. Okay. Okay. So, at t equal to 0, it starts with 0 0. When t goes to Tf, okay, let me write it properly. Okay. 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 When t goes to Tf, what happens here is that we are interested in taking this trajectory. I do not know how it will evolve, but ultimately this is, there is a 5 2 value, this is 5 let us say, and this is 2 basically. Okay. So, this point it does not have to go there, but it has to remain close to that value. Okay. So, that is what you are looking for actually. Okay. It need not go there per se, but there is a point phi 2, and this has to go develop and stay somewhere close to that point actually. Okay. That is the whole idea of that actually. Okay. If it happens to be exactly meeting, we are lucky actually, but in general it is not, we are not bothered about that, what I mean actually. So, what you are doing here? We start with a Hamiltonian definition. Hamiltonian is L plus lambda transpose F. So, that means L is nothing but this half u square plus lambda transpose F. F is F1 and F2 are there. So, lambda 1 times F1 which is x2 plus lambda 2 times F2 which is minus x2 plus u. So, that is the definition of Hamiltonian. Now, co-state equation tells us that lambda dot is minus del h by del x, that means lambda 1 dot is minus del h by del x1, and lambda 2 dot is nothing but minus del h by del x2. Okay. So, lambda 1 dot del h by del x1, it does not contain any x1 term. So, that is 0, and lambda 2 dot is del h by del x2, that means x2 is here, this is lambda 1, okay, and then x2 is here which is minus lambda 2, again take minus sign of that, that means minus lambda 1 plus lambda 2. Okay. That is how you get, I mean, co-state equation. Remember, state equation is already given, no need to derive it. Okay. So, this is there, co-state equation is already there by this algebra, and optimal control tells us that del h by del u has to be equal to 0. So, del h by del u is one term is u and second term is lambda 2. So, that means u is nothing but minus lambda 2, it is as simple as that. Okay. As long as we get lambda 2, we are done actually. Okay. That means, once is lambda 2 value is available, u is nothing but minus of that. It is very simple. It looks actually, it appears very simple at this point of time, but let us see how much effort is needed to get this lambda 2. Okay. Anyway, so u is nothing but minus lambda 2. So, I can substitute it here if I want to, minus x2 minus lambda 2 I can write actually. Okay. Anyway, so boundary conditions are like this, x1 of 0 and x2 of 0 are 0 0. And lambda 1 of 2, because remember the xf is free in a way, right, it is only close to that value, but it is, in truly speaking, it is free. So, we can talk about using the corresponding boundary condition which tells us lambda f is nothing but del phi by del xf. So, lambda f which is lambda 1 of 2 and lambda 2 of 2 is del phi by del xf, and what is phi here? Phi is this term. Okay. So, the lambda 1 f is nothing but lambda 1 f is nothing but del phi by del xf, that means del phi divided by del x1 f. So, this is first term, this is what it is. Similarly, lambda 2 of f Tf is lambda 2 of 2 is nothing but that actually. Okay. Now, how do we solve this equation? That is more important now. The differential equations, boundary conditions, everything is available, and our main aim is to solve for lambda 2. Okay. But we cannot do that in isolation, because lambda 2 dot what you see here is also a function of lambda 1. So, lambda 1 dot has to be accounted for basically. Okay. But fortunately, in this equation it so happens that lambda 1 dot is 0 That means lambda 1 is a constant value. So, that kind of gives us some simplicity actually. Anyway, we will not go through those details, but we will consider this something like a z vector. Z is contains x and lambda together. Z contains x1, x2 and lambda 2 together. Now, if you look at the differential equation, this is a linear equation and this is also a linear equation. Okay. So, I can put them together and write in the form of z dot equal to az, where a happens to be like that actually. Okay. Right. So, x1 dot is x2. So, this is what you will get if you get that. x1 dot is 0 times x1 plus 1 times x2 plus 0 times lambda 1 plus 0 times lambda 2. Okay. So, that is how you get that there actually. And similarly, all other things you fit it and then you will end up with this matrix actually. So, when you have this linear differential equation of this form z dot equal to az, the solution we know z of t is nothing but e to the power at times c. So, now you use the boundary condition at t equal to 0, okay, then t equal 0 e to the power at is identity. Okay. So, that is what you will do, then ultimately you get this c basically, e to the power at is I basically, right. So, we will end up with c. So, c1 and c2 happens to be 0 0 from the very first two conditions actually. Remember, this is 0 0 sort of thing, right. So, you have these conditions appearing that c1 and it will give us that c1 c2 is 0. Now, what about the other thing? Other thing has to be applied at Tf actually. So, when you apply a Tf equal to 2, we are looking for x1 of Tf, x2 of Tf and lambda 1 of Tf and lambda 2 of Tf. But lambda 1 of Tf is this one and lambda 2 of Tf is that one. We just derived this. Okay. So, this is what we will put it here and then write this equation again. Now, e to the power a Tf and Tf is 2. So, e to the power 2a essentially and a is nothing but that. So, you can evaluate e to the power 2a happens to be like this actually. Okay. Now, what? I mean, looking at this equation, what you are looking at? We are looking at variables as x1 of 2 and x2 of 2 and c3, c4. That means, this equation what you are having here is 4 equations with 4 unknown quantities. So, x1 of 2, x2 of 2 and c3 and c4. So, these 4 unknown quantities and 4 equations we can solve it, and while solving we have to rearrange these equations a little bit and we have to take this free variables into one side in the vector and all that. So, that we will do and we will end up with some equations like that. So, it is nothing but Ax equal to b form, we can solve it for that. Now, you get the values for x1 of 2, x2 of 2, c3 and c4 actually. So, you get the values of all that. That is where you will get the solution ultimately x1 of t, x2 of t, lambda 1 of t, lambda 2 of t. That is what your z vector, our z vector contain x and lambda together, right. So, we got the lambda basically in the process, lambda 2 what you are looking for we got. So, the control has to be u is equal to minus lambda 2 of t, that is what our main priority ambition was actually. Okay. But remember, to get this value it is so much difficult, because even though we started with a very simple looking problem and we observed that u is nothing but minus lambda 2, to get that lambda 2 is not that easy a process actually. It goes through a lot of algebra and then ultimately you will get it there. What about the second example, little more complicated? Well, I will not say that much complicated either, but it is more relevant to practical applications, which is like double integrator problem, x double dot is u. The relevance of that you can think about satellite attitude control problems without this damping terms and all that actually. We have this I omega dot is a function of something of a torque control torque in a different axis and all that way. So, this is double integrator problems are very popular primarily because of those kind of ideas. There is no aerodynamics, hence there is no drag, no lift, it is just a tumbling of mass basically sort of thing. So, that is how it is this double integrator problems are quite relevant in those kind of applications. But in general it is not true, I mean there are more complications and all, but approximately it is valid actually. This is the problem that we are talking. Okay, we want this double integrator system and we want to minimize this. Remember, final time is to be minimized as well. Okay, final time is not fixed here, okay, but Tf is unspecified. It has to be minimum time problem sort of thing you can think about, where it is not really exactly minimum time, but we want this Tf to be minimum, okay, along with the condition that control has to be minimum as well. So, that is why this control dependency is also available, I mean also part of the cost function. So, Tf is unspecified and control variable ut is unconstrained actually, that is what you are looking for. Okay. So, the double integrator problem happens to be like this. System dynamics is the linear form Ax plus Bu. Y is okay, again it not required really, but somebody can think of y as my x1 sort of thing actually. So, x dot is x plus vu, y equal to Cx, and the boundary condition is x of 0 is 10 0, x of Tf is 0 0. Let us say this is what here 10 is the angle and 0 is the attitude velocity, you can think. So, the moving the tumbling mass is some 10 degree deviation initially, let us say, and you want to bring it to 0 0 actually. Okay. That is what the object actually. First thing first is a controllability check. We should not forget that if the system is not controllable, you can't do anything. So, it makes sense to quickly do a controllability check for any problem. So, we do that, and then turns out that the determinant of m is -1, when more importantly it is not equal to 0, hence the system is controllable. When you can do that, we can proceed with our optimal control equations and all. So, first thing is Hamiltonian, which is half of u square, okay, coming from this term, okay, L, which is half of u square, plus lambda transpose f. So, lambda transpose f is nothing but okay, Ax plus Bu, okay. Lambda transpose f is nothing but x dot equal to f of xu. So, x dot equal to Ax plus Bu, that is what it is here. So, h is there like that. So, state equation already we know, co-state equation is lambda dot is minus del s by del x. So, if you see that minus del s by del x from here is nothing but minus A transpose lambda, only this term. And optimal control is del s by del u equal to 0, and del s by del u equal to 0 means del s by del u is nothing but u, I mean coming from here, okay, plus one more term V transpose lambda coming from here. So, u is nothing but minus r in, well, minus r inverse in general, provided you have this R matrix here, okay. But if R is identity here, so we will not worry about that. Talk about u equal to nothing but minus B transpose lambda, and B is something like this, B is matrix like this. So, if you substitute there, then again we will end up with u equal to nothing but minus lambda 2. But again, how difficult is that to get the lambda 2? Let us see that. So, these equations has to be satisfied simultaneously actually. Okay. We go through the optimal solution thing. So, lambda 1 dot lambda 2 dot is minus A transpose lambda. So, this is what in this form. The good thing is lambda 1 dot is 0. So, lambda 1 is nothing but a constant quantity, and lambda 2 dot is minus lambda 1. So, that is minus C1. So, lambda 2 happens to be minus C1 t plus C2 from this equation. So, u is nothing but minus lambda 2. So, it is C1 and C2. As long as we know C1 and C2, then our control is available actually. Okay. So, we go back to the state equation now and tell, okay, x1 dot is x2, x2 dot is u, and u is nothing but this, and hence a solution sense what happens to here, because x2 dot is available explicitly in time variable now, which is nice actually. Then I can talk about x2 is integration of that, which is nothing but this kind of thing, okay, C1 t square by 2 minus C2 times t plus C3. But x1 dot is x2 now. So, x1 dot is all that. So, x1 can be integrated again, and I will end up with integrating this one more time, and hence I have it actually. So, x1 of t is like this, and x2 of t is like that. Okay. Now, what about the boundary conditions? So, we will use the boundary condition at t equal to 0. So, that turns out to be like this 10 0, and hence we attempt to solve, I mean we got this C4 and C3 basically. So, that is eliminated, we are left out with C1 and C2 basically. So, this is like this. So, how do we get there actually? Now, we have to use this boundary condition for TF also. So, you use TF, and then this is what the result is, x of TF and x2 of TF is 0 0, that is what our aim is actually. Okay. Our aim is to drive it to 0 0, right, this is our condition actually. So, we put 0 0 here. So, this is the equation, okay. And what you observe here, the equation contains 3 variables C1, C2 and TF, when the number of equation is 2 actually. So, we really need one more equation. That one more equation is transversality condition, because TF is free, we can write it that way, del phi by del t is h of TF, and you substitute all the necessary things, you will end up with some constant like this. Okay. So, what you are looking for, what you are telling is, we now have 3 equations and 3 variables. Okay. So, there is a chance to solve it, but remember this is a set of equations that are non-linear now. There are terms like TF square C multiplied with C1, and then C2 TF square, C1 C2, all sort of things are there. So, essentially it is not that easy to solve it, but looking at this equation itself, you can think first two equations are linear in C1 and C2 at least. I can consider it as a equation for C1 and C2 which is linear. So, it is possible for me to write it in the form of Ax plus Bu sort of thing, and then try to eliminate C1 C2 as a function of Tf. Then I put that function in Tf here, whatever I get C1 and C2 and all that, and then I will end up with a huge polynomial expression for Tf and all. Okay, everything will be a function of Tf actually. Then I can find the roots of that and then get my Tf, and once I get my Tf, C1 C2 will be available. Okay. And ultimately, otherwise somebody can always think of doing it numerical solution way, taking the help of Newton-Raphson technique. That is also possible actually. Alright, so finally we will end up with some expressions like this if you do all that. Okay. And hence the control solution will be something like this. C1 and C2 was our primary concern. Okay. Well, this is a small mistake again. Okay, this is not U1, this is C1 and this is C2. Okay. So, C1 of t minus C2 sort of thing. So, C1 is like this and C2 is like that actually. And Tf is also available. Tf is nothing but that. So, you can calculate that. So, you can also tell this will not only arrest this tumbling, but it also take that much of time to arrest the tumbling. So, essentially it is an open loop control law because it is a function of purely a function of time, and the application of control has to be terminated at Tf. If you keep on applying this beyond Tf, then there is no guarantee at all actually. Okay. There should be a mechanism of stopping the control at Tf actually, that is more important. Another class of problems before we wind up this particular class, you can think that a function of state variables prescribed at fx prime of Tf and all that kind of thing. So, you have a function something like this, x dot equal to like that, j has to be minimized, where this additional constraint is coming into picture. Okay, this is an algebraic constraint, the function of states at Tf equal to 0 basically. How do you handle this? This can be handled with this auxiliary condition sort of thing, where we consider this further, some sort of a Lagrange variable, but Lagrange variable happening outside the integral. This happens inside the integral because of state equation, but because of this constraint equation, this gets coupled with this condition that you have, okay, which happens to outside the integral. Now, you can apply your regular optimal control, consider this as some sort of a phi function, and whatever you have here is something like a L function actually. Do that, this thing, what you are looking for, what you are looking here is very similar to the conditions, but lambda f will not be only a function of del phi by del x, but it will also contain this, okay, lambda f, and we will also consider this del j bar by del nu as some sort of a side condition actually, therefore. So, we have to solve both lambda as well as nu together since actually. Okay. So, a quick example of that is orbital transfer, where you talk about a rocket engine operating at some Tf and things like that. So, essentially some satellite was there or some orbit was there, and then it was to be transferred to a different orbit, okay, using the thrust force actually. Okay. So, the satellite has some thrust mechanism, it can operate anytime it wishes to. It starts here, and the ultimate aim is to merge with this orbit actually. The dynamics are satisfied, equations are like this. Okay. And then you can talk about system dynamics being these three, okay, and the boundary conditions finally, okay, initially the boundary conditions are the orbit 1 condition, and finally the boundary condition will be something like this. Okay, this uf has to be 0 ultimately, this perpendicular velocity has to be 0, and tangential velocity has to be maintained actually, that is your orbital velocity sort of thing. Okay. So, these conditions come as some additional constraint equation outside the integral actually. Okay. So, this equation, if you do that and algebra and Hamiltonian all that you define, and ultimately end up with this equation, this original equation, this co-state equation, optimal control and all that. And obviously, these equations cannot be solved using this pen and paper ideas in closed form. So, essentially the point here is, the message here, to get these values, what you are looking for is control value like this, but to get these values we certainly need numerical techniques actually. So, in general practically relevant problems will typically lead to numerical solutions basically. So, we have to gear up towards that. The boundary conditions are also split. So, essentially what you are looking for is this state equation, co-state equation, optimal control equation, and then boundary condition. It is a little bit complex condition. Conditions are there, the equations and conditions are available, just that it is not possible to solve it in closed form, and hence we need numerical solutions actually. Alright, so that is the message that I want to give in this class. So, we will see this numerical techniques and all in the next class actually. Thank you.